Okay, so this is Introduction to Image Processing. I guess it's called image processing, but really we're talking about digital images, which is the vast majority of images that you guys are probably used to seeing on your daily basis. And so today what I want to talk about is, kind of sounds like a dumb question. Where do digital images come from? And then what is digital image processing? So where do digital images come from? And what is digital image processing? That is, what are we going to be talking about in this class? Well, I mean, to the first question, it seems dumb, right? Duh, digital images come from a digital camera, right? You take a picture, that's the end of the story, right? But what I want to kind of talk about in the next, 20 minutes is that there are lots of ways to acquire images that either don't use a digital camera or don't even really use what you would think of as a camera at all, that still form a 2D or 3D array of pixels that we can treat as a digital image, right? And so there are lots of so-called image modalities that are other than the visible light camera on your smartphone, right? So certainly the most standard way is, to point number one, digital cameras, obviously. Duh. And so the way that kind of process works, and we're going to talk about this more a little bit next week, the image formation process, is that you've got some object in the world, and then you have a digital camera that looks at it, and then inside the digital camera is some sort of a array of pixels, usually a CCD array of pixels. And somehow the object kind of comes into the camera and it's imaged onto this tiny CCD array of pixels inside the camera. And we're going to talk in a lot of detail about exactly how that process works later in the class. Okay, so that's going to be a topic kind of for next week. But there are a lot of other places where you can get image-like objects, which I think we could just call digital images, that don't involve this notion of a physical object in 3D space that uses visible light to pass through a lens onto a CCD array, right? There are lots of other ways to get images, okay? And a lot of those things are outside of the visible spectrum, right? So all across the electromagnetic spectrum are ways that you can acquire image-like objects, okay? And so many of these, as we're going to talk about in just a second, are used for things like medical diagnosis and treatment, or things like baggage screening and cargo analysis, stuff like that. Those, if you have a truck that drives through a checkpoint, they're not taking a picture of the truck with a digital camera. They're taking a picture with some sort of fancy, non-visible spectrum imaging, right, to figure out what's inside the truck. And so let's talk a little bit about some of those things, okay? And I'm kind of going to go in decreasing energy along the electromagnetic spectrum. And so, actually, there is, there are a couple of good courses at RPI that talk a little bit more about the image formation process for different kinds of images. So, for example, Dr. Yazaja this semester is offering a course on radar imaging, right? So we're going to talk about that very briefly here, but there's a whole course on how do radar images get formed, right? Which is a totally different process than the way that images get formed on your digital camera in a CCD. So, okay, so let's talk about first, high energy stuff, gamma ray imaging. And so in terms of electrovolts, that's probably in the, millions or tens of thousands of electrovolts. And so in terms of medical imaging, the most common place where you'd see this is a patient or a subject is injected with some sort of a radioactive dye, okay? So you have a patient, and they get injected with some sort of a isotope. And after the patient has been injected, they start to give off gamma rays. And those gamma rays are received by a 1D or 2D detector. And this kind of imaging is used often for things like detecting infections or tumors, especially for things like bones, okay? And so as an example of what those images look like, here is an example. The top row is kind of like a lung image where you're seeing the gamma ray emission as kind of this pseudo-color red image, okay? The middle row, we're going to get to that in a few minutes, is a CAT scan, and the bottom row is superimposing the image from the top with the image in the middle, right? And so actually, if you've ever heard of SPECT imaging, so SPECT stands for single photon emission CT, computed tomography, or PET imaging, which is positron emission tomography, those are all variants kind of gamma ray imaging, okay? And so this is often used because the CAT scan gives you a sense of the structure of what's going on, but the gamma ray imaging gives you a sense of kind of like the behavior of what's going on inside the body, right? So you kind of get this functional and structural thing if you superimpose them on each other. And so here's another example again where you've got kind of the bluish thing is an X-ray or a CAT scan, probably a CAT scan here, and the hot spots are coming from some sort of SPECT imaging, which is telling you that, hey, there's something in the body at this location that is doing something abnormal, right? Some sort of bone tumor, for example. So here, even though the bone may appear as white in the CAT scan, it looks the same as every other bone, the gamma ray imaging reveals that there is something unusual about that particular thing, right? And gamma ray imaging is also used for cargo inspections. Certainly, all sorts of ports, for example, or borders have these non-contact big things that trucks and cargo containers are driven through, and that's used to detect any sort of radioactive material that's coming out of the containers, right? And so if you read a little bit about this, there are certainly lots of problems with false positives. So for example, cat litter and bananas apparently emit background radiation that is enough to get these things confused, right? But on the other hand, if you do have some sort of radioactive or fissile material, this thing will pick it up, right? And so this is one of the kind of first lines of defense of all the cargo containers coming into the country. These things are scanned for radioactive possibilities, okay? Okay, so next up is X-ray imaging. And so X-ray imaging is a little bit lower energy. Well, before I leave gamma radiation, I should just say that that's also used for astrophysical imaging, right? Because these celestial bodies are giving off radiation that can be detected with gamma rays. Okay, so X-ray imaging, you're certainly probably familiar with. I mean, I imagine that almost everyone in this room has probably gotten an X-ray, if not a full body X-ray, at least you probably got a dental X-ray, like those bite wings that you have to. I hate those. You put them, it's making me like a little nauseous just thinking about it. You put it in your mouth, they take the picture. I hate it. All right, so the way that those things work fundamentally is that there is, again, if we're talking about medical imaging, you've got a patient, and then you have, some sort of a source of X-rays. And those X-rays are basically, blasted through the patient. And again, just kind of like with gamma rays, there's a detector that receives the kind of, the number, the recipient of the detector is basically reflective of how much of those X-rays have been absorbed by the patient, right? So if the X-rays are passing through, thin air and there's nothing in the way, then they kind of arrive at full strength of the detector. If they're passing through solid bone or something like that, then they're going to be blocked by the patient and they're going to have a lesser response on the detector. And if the X-ray passes through, for example, something like your lung, which has got a lot of air in it, it's going to be a lot dimmer than something that passes through bone, for example. And so this is basically a projection. Of absorbed X-rays as they pass through the patient. And so again, you're probably used to seeing images like this. This is like kind of your standard chest X-ray. Sometimes you'll see it called a fluorograph. And so again, the spinal cord and the bones in the arms and stuff like that are soaking up more of the X-rays, and so they appear lighter. And then the lung, where there is a lot of air, appears to be darker, right? And so the advantage of this is that certainly you can tell if there's like some big tumor inside your lung, an X-ray may be able to pick it up as some sort of big mass that is visible in this projection, right? On the downside, all you get is this two-dimensional projection of what is fundamentally a 3D object, which is your body, right? So what you really like to get is more like a kind of 3D image of the patient instead of just one 2D projection. And so that's why, when you get an X-ray, you may get an X-ray from multiple angles, for example, to see if they can nail down what they're seeing. So this is a kind of a standard chest X-ray, hand X-rays for seeing if you've got broken bones. Dental X-rays, this is probably the most common thing. Actually, this is not your standard bite wing thing. This is the panoramic X-ray. I've never had one of these, but basically you put your head into some sort of thing, and you rest your chin on something, and this X-ray machine goes around your head and makes this whole thing. I actually would like to have one of these just because I can't stand the other kind. And also, X-rays are used in the airport for baggage screening, right? So when you put your bag on the conveyor belt as you go through security, that's an X-ray machine, most likely. And, since metal absorbs things at a much, different rate than cloth, you can see things standing out in the X-ray machine. So for example, here, this is like a backpack, and you can see that the zippers of the backpack and this gun and this circuit board and this knife and this pop can tab really stand out, right? Whereas it's like the cloth is like invisible to the X-ray. And so this is definitely another big reason why X-rays are used in real life. Okay, so let's talk about CT scanning or CAT scanning. So that's kind of a variant of X-rays. It's still using X-rays, but it's using lots of X-rays that are sent through the patient at different angles, right? So instead of just you standing and getting a single X-ray from one angle, you go into this machine, which I guess I showed here, right? And so what's inside the machine is, I should have stored a picture of it, is basically this rotating X-ray emitter along with a parallel aligned detector. And so that thing rotates around the patient and acquires lots and lots of projections, and those projections are then reconstructed to form the inside of the patient, as I'll kind of show you in just a second. So an important use of X-rays is CT, or computed tomography, scanning, also called CAT scans. And so the way that works is that, imagine that this is the cross-section of the patient, right? So maybe you've got their lungs and their heart. This is like a crude diagram, right? And so the patient is kind of lying on this couch, and then there's a X-ray source that is sending projections through the patient, and then this thing is rotating around, acquiring many different projections. And so it turns out that you can actually reconstruct a three-dimensional structure. In this case, this is like a 2D diagram, but in general, you can reconstruct the three-dimensional structure of what's inside the patient from looking at a whole bunch of these processes. And so basically the 3D image of object is reconstructed from many projections. And we're going to discuss that process in some detail probably later in the spring, March or April. So this process is probably the most mathematically intense chunk of the class, but it is interesting to think about, okay, well, how would you, kind of the intuition is, if you saw enough projections, it seems like there should be more than enough information there to get at what's inside. So we'll talk about exactly how that process works. And so, again, this is the machine that you'd go into, and these are the kinds of pictures that you would get. This is like an abdominal CT where you kind of see, as you take, it's almost like you get, slices of the patient. If you guys have ever seen like the Visible Man project they did at the NIH a long time ago, where they actually literally took, very thin slices of a person and scanned them in. So this is kind of what you get by doing it with the, machine. And so you can pick out all sorts of, structures. And in fact, a lot of my research has involved looking at these kinds of CAT scan slices and trying to automatically segment organs in them, right? So this is a process. This is a problem that we did for prostate cancer, several years ago, where I don't remember which one is which. I think the yellow outlines are what the doctor outlined in the CAT scan. The red outlines are what our automatic algorithm did. And so the idea being that can you try and interpret what's going on in the CAT scan automatically? CAT scanning is also beginning to be more used for baggage screening. So it's probably still true that if you go to your typical airport, like Albany Airport, I think is just standard, standard X-ray scanning. But in the back room, they may be doing CAT scanning of the baggage, and certainly of bigger airports, I think they're starting to do this. And so the advantage of this is that you can kind of rotate the bag in 3D and look at it from all angles and see this kind of pseudo-color image of what's inside. And you can imagine that's a lot more reliable for screening than if you're just seeing one X-ray projection of it. Okay. So let me pause and ask. Any questions about what I've said so far? Okay. So next is what I would call ultraviolet imaging. And so for those of you that are more kind of biomedically inclined, you may already be familiar with this kind of thing. So this is most often used in different kinds of microscopy, especially fluorescence microscopy. What that means is that you have some sort of a sample on a slide. And then here, this is like a sample that has got some sort of fluorescent dye in it. For example, there's something called green fluorescent protein. That's a very common dye. And then what you do is you shine UV light onto the sample, ultraviolet light, and then what comes off is visible light. That's what fluorescence is, basically lower energy photons. It's going from UV down to the visible spectrum. And so this is very common in terms of biological imaging of cells. And so, for example, you inject your sample with this stuff that glows green for different, and different components of the cell will pick up that green at different densities. And so, for example, this may be what you get from a fluorescence microscopy image, where each of these green blobs is a cell nucleus, for example, something like that, right? And it's even possible to tag multiple different fluorescences onto different kinds of cells or different kinds of proteins, right? So you could have something that fluoresces green, something that fluoresces red, something that fluoresces blue, something that fluoresces amber, like all at the same time, right? So it's kind of like this multi-dimensional, fluorescence problem. And so we definitely, I don't have a picture of it here. It looks like this. We had a professor here a few years ago, Dr. Roysam, who did all this stuff on biological image processing, and he had these great images of all these different UV fluorescence proteins that were fluorescing at different colors, and he had this kind of image processing or computer vision job of trying to figure out, okay, how do we automatically figure out where are all the cells, where are all the things that are connecting the cells, and so on. So this is definitely very cool stuff. In contrast, this is like a visible microscopy image. And so this kind of leads into what you're probably most familiar with is visible imaging, right? And so for that, I don't really have a lot of examples because you guys are so, awash in visible band imaging. That's what we deal with every day. So that's kind of at 1 electrovolt. And so what are some examples of, visible band images, right? So certainly, smartphones, basically any sort of consumer digital imaging. The image I just had on the screen was from a microscope. So basically, if you ever had a microscope as a kid, you were probably using light microscopy, where you basically stain a sample. Again, similar idea. The sample uptakes dye at different rates depending on what the properties of the sample is, and then you shine a light through it or you shine a light on it, and you see what's going on. Remote sensing, like satellite imagery, is definitely a big issue. So, and this includes infrared, I guess I'll say that as well. So infrared is just out of the visible spectrum, but it gives you information about, how hot something is. And so certainly everyone is familiar with, satellite imaging, like what comes from Google Maps, right? So this is from a satellite very high up, and you may be able to superimpose onto this, infrared imaging as well that gives you some sense of, what kind of terrain you're looking at, right? So different terrains give off different information in the infrared. Certainly there's lots of visible band imaging in things like manufacturing or industrial inspection. Right? So you have, conveyor belts with cameras that are making sure that the stuff that's going under them is appropriate. That happens constantly in industrial inspection. And again, we've got some visible imaging of this sort going on in like the CATS Center here at RPI, the Center for Automation Technologies and Systems. So there they know a lot about machine vision in the context of monitoring some sort of industrial process. Any sort of imaging off of a spacecraft, for example, would be visible imaging looking down at the Earth. You know, things like license plate recognition. Or biometrics, right? So for example, biometrics is stuff like this, right? So you are trying to extract some information about a person, right? Their hand shape, their retinal pattern, their iris pattern, their fingerprint, the shape of their ear even is very discriminative, how they walk, right? All that information is inferred from visible images, right? And so, you know, in this class, we're going to motivate almost everything that we do with visible images because they're easy to take and easy to analyze. But you know, that's why I'm going through the other stuff is that you know we can treat those other kinds of image modalities just like they were visible images. So yeah, so visible imaging is what we're going to talk about the most in this class, obviously. Okay, but we can go beyond the visible spectrum the other way, right? So far we kind of started out at gamma rays and went down to X-rays down to what we could see. Then you can actually go beyond what we can see in the other direction to basically microwave. Actually, in the middle of that is what you call millimeter wave or terahertz imaging. That's just below the visible spectrum. And so, again, this is kind of conceptually, it's kind of, or not visually, conceptually it's kind of similar to what you get like in a X-ray kind of thing. There was a professor here, XC Zhang, who did terahertz imaging a couple of years ago, and that's also a valuable modality because it can kind of, you know, penetrate a little bit, enough to be able to tell, for example, whether you've got like a weapon under your clothes, for example. And so if you go, I guess I should be careful what I say. So at the airport, you know, the thing that you have to do this and the thing that cycles around, I'm trying to remember whether that's a millimeter wave imaging system or not. I think that it is. But there was another kind of millimeter wave imaging system that was like found to be useless at the, you know, at the airport level, and so they started to take those out. So let me go back and think about what this thing is. But I'm pretty sure that is at the millimeter wave level. So below that is microwave imaging. So you go from millimeter to micro. And that's where you get into stuff like radar. And so, again, here's a case where there's not really so much of a image per se, but what you're doing is you have some sort of a emitter that is sending out a microwave pulse. And it hits an object, so, you know, this is like a really crappy airplane, but all right. So it hits the object, and then based on whether something returns and the time of delay of the return, you can infer what's out there in the sky. I mean, not only what's out there in the sky, but also what's on the ground, right? So certainly radar is used both standing on the ground and looking up. That's kind of the more military application. And sometimes you'll even see planes, like if you've ever seen the plane that has like the big kind of weird cylinder on top of it, that's got a radar inside of it. It's probably trying to do radar imaging in the sky to other aircraft, right? But certainly you can point a radar imaging system down and get terrain models, right? So certainly if you've heard of like synthetic aperture radar, this is that kind of thing, right? So you can get these very nice detailed terrain models. You can get, again, this is like a pseudo-color image of a radar image looking at the ground. Yeah. Okay. So then we come to radio band imaging. And that's where we have things like the MRI, which stands for magnetic resonance imaging. And so again, in this case what's happening is that you have, again, a patient lying on a couch, and then they're surrounded by this huge magnet. And the magnet is basically pulsing radio waves into the patient, and those waves are being reflected and detected. And so the way that the way that the radio waves are reflected and the strength with which they're reflected is something that allows you to generate, again, a kind of a detailed 3D model of what's going on inside the body. And so you get images that look like this, right? Very detailed, and one nice thing about this is kind of what they call non-ionizing radiation, right? So it's not like you're pumping X-ray radiation to the patient. You're getting this very nice kind of detailed image. And then there's a kind of a extension of that called functional MRI, right? Where here you can also kind of say, okay, it turns out that oxygen in the blood uptakes it has a kind of, I don't remember exactly how this works. Basically, the spin or something of the electrons is different for oxygenated blood versus non-oxygenated blood, and so you can basically infer where is the blood pumping inside the body. Then you overlay that on top of the regular MRI image, and you can tell, okay, if you ask someone in this MRI tube to do some sort of a task, you can see what parts of their brain light up, right? And so again, there are people who are working on fMRI here, and here you probably can't read this, basically the caption of this, the top one says physically induced pain, and then the bottom ones say hypnotically induced pain. And so this is a study where basically, they're trying to tell, is there a difference between the way that your brain reacts to real pain versus, pain that's not actually occurring to you but is being induced in you by hypnotism. So, this kind of analysis is also very interesting. And again, you get this kind of 3D image with the functional part superimposed on it. Okay, then you can get stuff like ultrasound. And so ultrasound is something that is not technically inside the electromagnetic spectrum, right? Because there's no energy wave in ultrasound. That's a pressure wave that's created from sound, right? And so instead, what's happening with ultrasound, I would say, this is like imaging without photons at all. So everything we talked about so far, there's some sort of a photon with some sort of energy involved in creating the image. Here, there really isn't any sort of, there's no photons at all. What you have is a patient, and you have kind of like an ultrasound probe. And this thing is basically pulsing sound waves that you can't hear inside the patient, and basically structures inside the patient are bouncing back to the detector. And so this is usually a lot less of a high-quality image than a CAT scan, for example, or an MRI scan, but it's much quicker. I mean, you can basically do it kind of on the fly. You see all these, images of pregnant women getting kind of like the real-time image of what's going on. So in some sense, it's nice for kind of quick and dirty imaging. And you could do some sort of, automated understanding of what's going on in these images too, but they're a lot kind of grainier than the images that you get with ionizing radiation. And finally, I would say, another non-imaging or non-photon related modality is something like electron microscopy. So if you ever heard of like a scanning electron microscope, how that works is basically you have a sample and you're throwing electron beams at it. And the sample is basically kind of soaking up or diffracting the electrons, and then you have a detector on the other side. So this is actually kind of similar to X-rays, but with electrons instead of with X-rays. And finally, there are lots of images that we can create on our own that don't come from like a single emitter, detector, or sensor, but images that we synthesize as humans, right? So for example, a very common thing is something like, this is a map of I believe the ozone layer. It says nitrogen dioxide. This is like a pollution map over the United States, right? So this is data that is superimposed on a map, and now you can imagine wanting to use image analysis techniques to understand, where are the hotspots of this pollution. Or, weather maps. So our weather map is going to look pretty bad in a few hours, but this is another example of where you've got returns, probably from radar, that are superimposed on a map, and now you could process this image, kind of jointly with both the color and the images. Or you could have something that's like entirely like data-driven. Like this is like census data of where people use the word dude versus bro, right? And so you could find the dude concentration. Or this is an example from, there was this thing that was making the rounds a few months ago about how you pronounce certain things, right? So this is how you pronounce the thing that you go get a drink from in the hall, right? So here we call it a water fountain. I'm from Wisconsin, and so I'm in that green spot where we called it a bubbler, right? So I'm the only one who would call it a bubbler, although I don't really call it that anymore, right? So these are all images that, again, these are not taken with any camera, but they're still images that we can analyze and understand what's going on. Okay, so let me talk a little bit about what we're going to talk about in this class. So before I go into that, so any questions about any of the, what I just talked about what I would call different imaging modalities, okay? So there are now you know at least 10 different ways of getting digital images aside from how to do it on your camera phone, okay? So questions or comments? And so let me just say that this is immediately like a good time to start thinking about, obviously I haven't taught you any image processing yet, but when you think about your project, for example, you don't have to do a project that's just related to images that you take with your phone, right? So you can do a project on biomedical images, biological images, satellite images, X-rays, CT scans. So I mean, I welcome projects that are not in the visible spectrum. The only thing you have to think about, and if you're going to do a project like that, you should kind of get started on early, is where you're going to get the data from to do that project. So if you want to do a project on CT scans, for example, you'll find that it may not be so easy just to Google CAT scans and grab like full CAT scans off the web, right? There are privacy concerns, there are huge data sets, and so I mean, if you want to get into that, we should talk about it earlier rather than later, and I may be able to point you to different professors on campus, for example, who may be able to give you images that have certain characteristics. Okay, so let's talk about what we're going to talk about in this class. So digital image processing. Okay. So I think that there are different levels to this problem, okay? And so what we're going to talk about first is what I would call low-level image processing. So this is like, pre-processing the image to remove noise, sharpen it, or enhance an image. And so generally the way I think about this is the input is an image and the output is an image. Okay? And so for example, this is kind of like a low-level image processing problem, right? I've got a blurry image, I want to apply some sort of image processing technique, and I want to sharpen that image up, right? So we're going to talk about that process for sure. I mean, this is kind of an idealized case. I mean, certainly it seems like it stands to reason that if I have blurred up an image, I've lost the high frequency information or the high detail information, but I probably would not be able to get back this great image, right? In fact, I just showed you this image and I blurred it and I showed that first, right? So, but you can, it turns out that if you know how the image was blurred, you can do pretty well in recovering the sharp image. You'd be surprised at how well it can actually work. And so we'll talk about that a little bit. Okay, so but I would call this a low-level task in the sense that, I started with that blurry image, I got a resulting image, right? And so the same thing would apply, for example, if this image had like, noise in it, if it was tilted and I needed to, rotate it, if it had poor contrast and I wanted to make the colors pop better, all those things I would consider to be kind of low-level image processing tasks. Not to say they're not important, but they are kind of like processing pixels to produce other pixels, okay? So that's probably going to be the first, month or so of class. And then I would say there are mid-level image processing problems. And so that's stuff like, for example, segmenting an image into, regions or objects, describing an image concisely, and the way to think about this is that you start with the image, and what you come out with are things like attributes. For example, edges, lines, objects, or maybe it would better say regions. Right? So to kind of look at our image here, that would be like saying I take this image and I try and find the edges of that image, and I end up with a binary image that looks like this, right? And so you can see that, for example, since the border between this white paper and the black table is a big difference between white and black, I can really pick out that edge automatically, whereas the edges inside the strawberry are a little, there's lots of different colors inside there, and when I try and do edge detection, I maybe get a little more of a mess, right? So this is still like the first building block to trying to understand what's going on in the image, right? So it may be that if I had, cells on a microscope slide, I could find the edges of the cells, and I could find their boundaries, and that would be the first step to understanding what's going on in the image, okay? So again, what I've done is I've taken the image initially, and I've produced kind of a description of the image that is not just pixels, but is more like primitive objects, right? Here I'm talking about edges, but for example, if there were long straight lines in this image, so for example, this would be pretty tough, but suppose I was trying to find the orientation of the picnic table that this image is taken on, right? I could try and detect these long straight lines and superimpose those on the image, right? So for understanding like an urban scene, I might want to find the edges of buildings and windows in order to determine vanishing points of where the camera is looking, for example. So we'll talk all about that, and that's kind of like the second chunk of the course. And then the third thing is what I would call kind of high-level image processing. And in general, I would call that kind of making sense of an image. Image understanding, and what I would call computer vision. Right? And so, for example, a computer vision problem would be something like, taking that image and understanding that, this is a strawberry, right? Now, we're not going to be able to get to that point in this class. So in some sense, the way I think about this class is giving you the building blocks that you need to go on to a course like the courses that are being offered right now in computer vision in our department and the CS department, right? So you certainly have to know how to push pixels around and analyze them before you do serious computer vision image understanding projects, right? And so, again, there may be some of that later in this course, and it could be that you get into some of this for your project. So for example, maybe you could apply a face detector to take an image of this room and then automatically decide which pixels in this image correspond to faces, right? But something like face recognition would be even higher level than that, trying to understand not only that this is a face, but that this is, Rich Radke, right? That would be something that is more of a computer vision problem that requires a lot more understanding and a lot more data, right? But this is where we would be going, right, with the tools that we learned in this class. Okay. So questions or comments about that? All right. So let me just drill down a little bit into the topics that we're going to talk about this semester. Okay. So let me just say major categories for this course. So the first we're going to talk about is image acquisition. And that kind of thing is like, how does the, first of all, how does the human visual system work? So that's going to be the next class, which is not really about digital images at all, but it's about how we as humans understand and perceive and represent things like color and intensity and brightness and so on. And that stuff is actually really interesting to think about how your eye and your brain work together to actually make the images that you see in your head, right? So we're going to talk about the biology of that a little bit, the perception of that a little bit first. Then we're going to talk about how do digital cameras actually, gather light from the world, put it onto a CCD, and produce the pixel values, right? So what is the actual process of producing that image that you go from the camera to the image in Photoshop? What's happening? And also we're going to talk about how do things like CAT scanners work. So for example, when we get back to the talking about the X-rays and the CAT scanning, how does the, how do we actually model this process of projection of, rays passing through a body? Okay. Then we're going to talk about what I would call image, manipulation, manipulation and enhancement. And so this is basically, the kind of thing that you would do as a amateur in Photoshop, right? You take a picture, you say, I don't really like this picture so much. I wish it was more contrasty, or I wish it was brighter, or I wish it was rotated a little bit so that the horizon line was parallel to the ground as opposed to tilted like this. So this is basically the process of tweaking an image in the way that you would tweak it in Photoshop. And I guess I would call this the subjective process. So things like geometric operations and photometric or grayscale or color operations, right? So how do I make the image look better to me, okay? And so you guys are probably already doing that in the real world. Then I would say there's what I would call image restoration, which is a little bit more specific and a little bit more objective than just enhancing it, right? So for example, if you know that the image has been blurred, and if you have an estimate for how the image was blurred, right? So for example, if I'm taking an image of a street scene and I move, my hands are shaking, right? I take a picture at night, I can't get a lot of light into the camera, and so what I get is this kind of, shaky image, and maybe this, lamppost gives me a little jaggedy line instead of being a dot, right? That jaggedy line kind of tells me, or gives me a clue for how did I move the camera, right? And so if I know what the blur applied to the image was, I can try and undo that blur to get a sharper image, right? And that's a case where there is a right answer, right? There is an objectively right answer that comes from, if you remember from DSP, we talked about Wiener filtering, right? Which is probably a lecture that you guys don't remember, but something like, if I know how a signal has been degraded, what's the best possible filter to apply to get a desired signal, right? That's exactly the kind of thing we're going to do, but with images. And I think that actually doing it with images will make the Wiener filter from DSP a lot more concrete, right? Why do you want to do this? Well, the desired thing is the unblurred image, right? Then we have, I guess what I call image reconstruction. And that's what I would talk about, like how do these various CAT scans work, so we're going to spend probably about a week on that. Image compression is kind of a fun topic. So basically, you are familiar on the web with all sorts of file formats, right? So what is the difference between a GIF and a JPEG and a PNG and a bitmap, right? Why are some of those images bigger file sizes or better fidelity than others, right? So we're going to drill down into how do these image compression standards work, right? Some of those standards are lossless, meaning that you can compress the image and be sure that you got exactly the same pixels that you started with, and some of them are lossy, which means that you are changing the pixel values a little bit, but you're doing so at the benefit of getting much better compression ratios, and the image looks almost the same, right? So for example, a JPEG image is a lossy compressed image, but it looks pretty good compared to the huge bitmap or raw file that you would get from your digital camera, right? So we'll talk about that. Then we'll talk about image segmentation. And that's along the lines of what I was talking about if you were looking, for example, at a, well, this actually covers lots of stuff. This is kind of like, edges, lines, objects. So how do I actually find these primitives in the image, right? And so that's kind of the first step up the ladder towards this mid-level image processing, right? So certainly we're going to talk about things like detecting long straight lines in images, and then detecting things like, blobs in images that may come from cells on a microscope slide, for example. And then as we go a little bit further, I'll definitely talk a little bit about image kind of understanding and computer vision. I mean, since this is what I do, I'll talk a little bit about some of these topics. So for example, how do these algorithms work where you say, I take a picture and I say, this is a person, this is a car, this is a street lamp, that kind of thing. And then towards the end of the class, like I said, the last 3 or 4 weeks are going to be what I would call kind of advanced topics. And since I wrote a book on computer vision for visual effects, I'm going to draw a lot of things from what I wrote in my book about that. So I mean, there are kind of things like how do you compose images. So when you see any single frame of a movie is a composite of many, many elements, right? Actors who have been shot on a green screen, computer graphic, backgrounds, real props, artificial smoke and stuff like that. And so how do you take all these disparate elements and composite them into the same image to make that image look realistic? How do you hide the seams when the image has been manipulated, when you've butted 2 images up against each other, right? So I think that'll be a lot of fun because that's something that we all can appreciate from TV and movies. And so if you look at the last chunk of the lecture, that's going to have things like image blending and combining images, reshaping and resizing images. So for example, I took a great picture and now I want to get the best possible version of that picture for my smartphone that has a totally different dimension display than the original picture. How would I do that? Then we're going to talk a little bit about things like image watermarking, even things that are related to like image printing, right? So how does the, when you have a newspaper, right? So clearly you can only put splotches of ink on the paper, yet it seems like it's grayscale, right? So what is the process of actually half-toning an image in both grayscale and color to be able to make it look like it has all these shades of gray and shades of color? And so I think that stuff will be interesting, and that will all build on what we talked about earlier. Okay, so any questions or comments about what we're going to do or what we're not going to do? Okay, so that's about it for the first day. So what we're going to talk about next time is, again, the human visual system. And so that I think will be interesting. We'll learn about how your eye works and how you perceive color. If you want to read up on that initially, so on Piazza, there's already a couple of links there at the bottom of the resources page on optical illusions and kind of visual phenomena that you can take a look at. And we'll look at those in class. But definitely, sometimes the images that we're going to show on the big screen here